Okay, now that we know a little bit about Newton's second law, I think this is an appropriate time to take a look at a couple different types of forces that are known as resistive forces. They're called resistive forces because they resist motion. You can see the root word here, resist. They resist motion. So the two categories of resistive forces are friction, or specifically sliding friction is what we're going to be discussing. And the other one is drag forces, and specifically what we're going to be talking about as a subset of drag forces is air resistance. Air resistance. There are other drag forces. For instance, if you're driving a boat through the water is going to exert a drag force on the boat. That would be a water resistance force, but we're going to be focused on air resistance. So these are the two that we're going to discuss. I'm probably only going to get through, my guess is I'm only going to get through sliding friction in this video, and then air resistance will be a later video. So let's take a look at sliding friction. And sliding friction, I will warn you, is a little bit complicated because there are two different kinds of sliding friction, and you have to be very careful about knowing which type of sliding friction you're dealing with. And so to illustrate that, I want to imagine the following situation. Let's imagine that we've got a surface here, and we won't specify this as a frictionless surface. We'll imagine that this surface has friction. And there's a block at rest. So here's this block, and we're told that V initial, well, maybe I'll do that later. So here's this block, and it's on the surface here. I guess we can do this. So we'll say V initial is 0. So it's at rest, and I come in and I push it. So I apply a force, this applied force. And what I'm going to do is I'm going to vary the applied force. So I'm going to start really small with my applied force, and then I'm going to gradually push harder and harder and harder and harder and harder. So I'm going to gradually make this applied force bigger and bigger and bigger and bigger and bigger. And you can see what's going to happen. Initially, when I push it, if I don't push it hard enough, if I push it gently, not hard enough, the block won't move. And if I push it a little bit harder, maybe it still won't move. And if I push it a little bit harder, it still won't move. And then eventually, you're going to reach a point where it starts to slide. You're going to reach what's called the breakaway point. So that means that there are two types of friction going on. Because when it's not moving, when the block is static, or stationary, stationary, there's a type of friction called static friction. In other words, I'm applying a force here, but the block doesn't move because there's a friction force acting backwards here that's opposing my applied force. But then eventually it will start to move, and beyond that there will then be a friction force that's associated with the moving object, and we call this kinetic friction. So we have two different types. There's a static friction force and a kinetic friction force. And the static friction force is always bigger than the kinetic friction force. So maybe I'll just kind of throw some labels here. Static friction, I will abbreviate this as F sub S, and I will abbreviate kinetic friction force little f sub K. And it is always the case here, we will see that that's a little f. Fs is always bigger than Fk. In other words, it's all, and you might realize this in your everyday life, that if you see a heavy object and you try to push it, it's always harder to get it going than it is to keep it moving once you've gotten it moving. Getting it to budge when it's at rest can be, in some cases, really, really hard because the static friction is more than the kinetic friction. To understand why that is, it might be worth thinking about where friction comes from. So let's imagine we zoomed way, way in. What's going on the ultra microscopic level? Well, if we could zoom in really closely on this, what we would see is that even a surface that appears to be smooth isn't smooth. You would see that the bottom of this block has these little bumps in it. And the table also, or the floor, whatever this is also going to have all these little bumps. And then what happens here is as one surface, let's say the block is trying to go this way, if the block is trying to go this way, or indeed even if it is moving to the right in this case, you can see that each and every one of these little bumps here is going to get snagged up with the bumps on the other surface. And it's that snagging, the sticking of these bumps, these ridges against one another, that's going to cause the resistance that we call friction. And every surface, no matter how smooth it may look, is going to have these little bumps. So you're always going to get this friction here on this, due to this ultra microscopic, or sometimes you can actually see it, right? If you look at like sandpaper, it's fairly obvious. So that means we've got these two different types of friction. Again, we've got the static case and then we've got the kinetic case. We know that static friction is going to be more than kinetic friction, but how do I actually calculate them? What sorts of things go into finding the amount of friction? So I'll put this under the heading calculating friction. Friction forces. And we're going to have two different ways. We're going to have one way for the static case, and we're going to have a separate way for the kinetic case. So let's start. Maybe we'll start with, I guess I'll start with static. Static is the tricky one. So I can tell you right now that kinetic friction is easier than static friction. And the reason is, let's imagine I go back to this case right here. What if or maybe I'll just actually redraw it over here. Let's imagine that I have that block. So here's the surface and here's the block again. And what if I tell you that I apply an applied force of 10 newtons, and still the velocity is 0? In other words, I apply a 10 Newton force and the velocity is 0. Well, what does that mean? Well, that means that the friction force, the static friction force, has to also be 10 newtons because it didn't accelerate. And now you could see where this might go. I might go ahead and maybe make the applied force, 15 newtons. And if it still doesn't move, the static friction force is 15 newtons. And then if I apply a friction force of 20 newtons, and it still doesn't move, the friction force is 20 newtons. So what I'm getting at here is that the static friction force can vary. In this particular case, it could have been 10, it could have been 20, it could have been 15, it could have been any of the values in between those as well. But there is going to be a maximum. So you are going to get to a point, let's say I get magically to the point where, let's say I apply a force of, say, 25 newtons, and now the velocity isn't 0. Now it's going to start to move. So maybe this then is the maximum case. Maybe this is that special case where anything below 25 newtons and that block won't move, but if I reach 25 newtons, boom, the block will go. That means that I have reached the maximum static friction force. In this case, in the example I was giving, would have then been 25 newtons. So the static friction force can vary. And that makes it harder. Variable. So the way we write this, or the way we'll put this, is I'm not going to write an equation, actually. I'm going to write an inequality. I'm going to say that the static friction force is less than or equal to something. So in this case, the static friction force, when I was going through this, was less than or equal to 25. It could have been 10, it could have been 15, it could have been 20, but the maximum is 25. So what goes on the right-hand side of the equation? What are the things that go into figuring out how much friction there is? And there's only two things. That's the good news. There's only going to be two items on the right-hand side of that inequality. The first thing, which might be obvious, is how rough or smooth the surfaces are. So maybe I'll just sort of note this over here. So two factors influencing or affecting the friction force. And the first one is how smooth or rough the surfaces are. If they're rough, you're going to have more friction, stands to reason. If they're smoother, you're going to have less. And the symbol we use, the way we write how smooth or rough it is a Greek letter which is called mu. This is the Greek letter mu. I want to kind of zoom in and kind of take a look at this. This is the Greek letter mu. And it's almost like a U with a long tail in the front, like this. That's the Greek letter mu. So mu values are usually less than 1. They're usually between 0 and 1. They can be more than 1, but it's not common. And a small mu would mean a smooth surface, and a rough mu would be, if their surfaces are rough, that would be like a large mu. So, if it was like 0.05, that might be two very smooth surfaces, and if it was like 0.7, that might be two very rough surfaces. So, over to my equation here, I'm going to put Fs is less than or equal to mu, and the other factor is how hard the surfaces are pressed together. How hard the surfaces are pressed together. And the reason that maybe makes sense if we go back up to our explanation on this microscopic level. Again, we're thinking about snagging between these little bumps, right? And if I press these surfaces together, if I exert forces like this, if I press the surfaces together, these little bumps are going to get snagged on each other even more. So more force between the surfaces is going to cause more friction. And this is the force between the surfaces. We have a name for that. That's the normal force, F sub n for normal force. So the other factor that goes in here is F sub n, the normal force. So I'm going to say the static friction force is always less than or equal to mu, the coefficient. I should say this word. Mu is an abbreviation for something. Mu is the abbreviation for something called the coefficient of friction. So if you hear me say coefficient of friction, that means mu. That means this guy here. So the static friction force is less than or equal to the coefficient of friction mu times the normal force, which means then I could say Fs max, the maximum force of static friction, is exactly equal to mu times the normal force. Sometimes what we'll do here, and you'll see me do this, is I'm going to put a little subscript s in here. And that just reminds me that we're in a static situation. Okay, so that's the stationary or static friction force. Now the easier one is the case of kinetic. And kinetic's easier because it's just a constant value. It doesn't vary. Constant value. So to calculate the kinetic friction force, which is F sub k, that's simply equal. I don't have to do an inequality. I don't need less than or equal. I can just say equal to, and it's just the same exact values, mu times the normal force. And the only difference here is that rather than mu sub s, up here we have here now mu sub k. So there are actually two different mu's, two different coefficients of friction. One for the static case, and then one for the kinetic case. But what really makes kinetic friction easier is this idea that it is constant, that it doesn't vary. Okay? And again, just like we said, we noted earlier that the static friction is more than the kinetic friction. That is ultimately because the mu sub s will be greater than the mu sub k. Just to see how this would work, let's imagine that this is a, let's say that this block back here that we were talking about earlier, let's say that the mass was 5 kilograms. Okay, so that means that the force of gravity, mg, is, let's just call it 50. I'm using g equals 10, so m 5 times 10 gives me 50. that would mean that the normal force here, F sub n, has to be 50 newtons as well, right? So what does that mean? Well, that means if I've got a normal force of 50, and we found out that Fs max was 25, then that means that to find my mu, I could say, I can go and use this equation right here, and I could say that if the maximum force of static friction in this previous example was 25, and the normal force in this case was 50, then I can see that I'm going to end up with a mu sub s of exactly 0.5. That would be an example of how we would find a mu value in a problem such as this one. Just to see how a problem might work with kinetic friction, let's again go back to this problem. And I applied a force of 25 newtons again, just to look at this situation. We apply a force of 25 newtons, and then the object starts to move. So now I'm in a kinetic situation. And maybe now I'll provide you an additional given. We just noted moments ago that mu sub s is 0.5. Let's imagine, just to make life easy, what if mu k happens to be 0.1? And now if I were given the mu k value and we keep this applied force at 25, I can find the acceleration of the block. So here's what I'm going to do. Then I would say that now, in this case, we've got now not Fs, but we've got now Fk. Here we go, Fk. And I could figure out what that force of friction is. Fk has got to be mu k, 0.1, times the normal force, which is still 50. So now I would say Fk equals, maybe I'll actually free up some space. Hold on, here we go. We'll say Fk is equal to 0.1 times 50, which then is simply 5 newtons. So now we can see that this block will accelerate. Why? Because I've got an applied force of 25 newtons still, but now the backwards force is only 5 newtons. So I can go ahead and use my F net equals ma equation, and I'm going to say F net equals ma. The net force is going to be 25 minus 5. I always do bigger minus smaller. And that's equal to 5 times a. So 20 equals 5 times a. So a is going to be 4 meters per second squared. That would be the way you would use the kinetic friction equation in a simple example. You'll have plenty of opportunity to practice friction on the problem sets.